שלום לכם, שמי נדב שנרב, מניח שיצא לכם כבר להתקל בי פה, ואם לא אז משתתף בצערכם עכשיו. אנחנו נמצאים בקורס מתמטיקה לפיזיקאים לתואר שני. אני מניח שרובכם פיזיקאים לתואר שני שרוצים לדעת מתמטיקה. רגע, שפה, יש פה מישהו שאינו דובר עברית?
אני מדבר אבל לא טוב.
אז אתה מעדיף שהקורס יהיה באנגלית? כן? אוקיי, אז תוך כמה דקות אנחנו נעבור לאנגלית. We will switch to English in a few minutes.
נזכור אותו אחר כך.
What? אוקיי. בסדר? רגע, ראיתי שיש סטודנט בינלאומי שרשום לקורס, זה אתה? אוקיי, whatever. מיד, in a moment I will switch to English. Just I want the administrative announcements and that to be in Hebrew. כן, עכשיו אני נכנסתי לרזוננס. אוקיי, אז בעצם מבחינת מנהלות אתם כבר ילדים גדולים, יודעים שם המשחק, יש לנו פה קורס, בסוף הקורס יהיה מבחן, הציון מורכב אם אני זוכר נכון מ-80% מבחן, 20% עבודות בית. וזהו בעצם, הקורס יתקיים כאן כל הסמסטר. אני כתבתי לכם היום במייל כתבתי שרק היום הקורס יהיה פה, אבל הוא יהיה פה מעכשיו עד סוף הסמסטר. שמו אותנו מה שהיה כתוב במחשב, בהודעות של האוניברסיטה, זה החדר פה בהמשך 303 שאין בו לוח, ואני מעדיף ללמד עם לוח, לכן עברתי למקום הזה. ומה עוד יש לי להגיד? זה פחות או יותר. איזה שהן שאלות על שאלת המנהלות? לא. אוקיי, אז so let's switch to English. To begin with, I would like to start by giving you. I mean, it's always good to use anecdotes, right? Because the students are not going to remember anything but the anecdotes. Yes, maybe there are students here who learn electromagnetism with me like 2 or 3 years ago, and I'm sure they don't remember what pointing vector is, but they do remember what I told them about the politics in Congo. Right? So please disturb this thing among your friends. This is okay. Each one has one. It's not so important, but this is a matzeva. It's a gravestone of somebody somewhere in Israel. I don't know where. And what is written here that this guy was a poet and mathematician, and he took with himself to grave the secret of solving this equation. Okay, it's a true צילום אמיתי, מצבה אמיתית של בן אדם. And okay, so one of the goals of this course is to help you not to have such a writing on your gravestone, because the answer to this is x equals to 1/2 of the square root of -73 plus 28 times the square root of 10. You can check by substitution that this is the solution, right? So I don't really know what's the background for this weird gravestone, but as a matter of fact, it's not.
That's the only answer?
What?
That's the only answer?
I think so. At least this is one of the answers. Yes. And the point is that this is fourth order equation, right? And it's solvable because fourth order equations are, we have a solution. Like second order equation have a solution, we have a solution for third order equation and for fourth order equation. But fifth order equations and above are not solvable. Right? So this is not a big trick. This is a fourth order equation, and as you can see, it is solvable. This is a solution. Okay. So, so now the point is that I want you to remember that there are two types of questions, or two types of mathematical problems we encounter as physicists. What are the two types? Solvable and not solvable. Right? So this was an example of a solvable question, solvable equation. Okay. Now to the one of the dark secrets of our profession. So because this is a course for second for master's degree, so you all of you, I guess, have a first degree already. So after you spend the money, I will tell you the sad truth, which is that first degree in physics is sort of a bluff. And why? Okay, there are many very important things that are taught in first degree in physics, but in one very critical point, your teachers until today, including myself, were cheating on it. And this critical point has to do with the use of solvable equations, right? Because when you get homework at the mechanics course, you have an equation, right? You have some equation, and you translate it to an equation, and this equation is solvable. Why? Because nobody will give the students in the first year a non-solvable equation, right? So clearly, however, the generic equation is not solvable, right? If you have, for example, second order equation of the form a of x y double prime plus b of x y prime plus c of x y equals 0 even, linear, homogeneous equation, for generic choice of a, b, and c, this is not a solvable equation, right? So all the equations and all the mathematical problems that you encountered during the last 3 years were solvable. Why? Because this is a pedagogical requirement. We cannot give first year students non-solvable equations for homework because they will run in screaming and yelling into the darkness of the noon. So this is not, we are not allowed to do that. But as a matter of fact, when you start working on real problems, you find yourself with a generic situation, and in the generic situation, you find yourself with a non-solvable equation, non-solvable polynomial equation, non-solvable differential equation. The generic equations that we physicists encounter in life are not solvable. Okay? And the question is, what to do? Right? What can be done when you develop a theory for whatever on earth, and you find yourself with a fantastic equation, maybe very simple in shape, but still not solvable. Okay? Okay, so there are exactly 2 ways to continue, except of quitting physics, right? 2 ways to continue. Once you encounter an unsolvable equation, there are 2 ways to continue from this point. One is to do numerics. And you all know the problems with doing numerics. It's a non-generic, you have to plug numbers, and then you don't know what's happened if you change the numbers. If you have taken delta t to be 0.01, and instead of it you will take delta t to be 0.001, maybe it will change completely the answer, right? You have to plug numbers and to believe that somehow the simulation reflects the generic behavior of the system, which sometimes it is and sometimes it isn't. And the other route is perturbation theory. And this is the topic of this course, right? The topic of this course is to give you the tools to attack any problem, to hit every problem, no matter how much it is not solvable. You will get the tools to do something to it. Maybe it will not help, but at least you will get the way of doing something with non-solvable problems. During the course, we will discover many interesting points, including the fact that to some extent non-solvable problems are easier. The non-solvable equations are easier than solvable equations in terms of the physical information we want to gather from it. I will explain you why during the semester. And there are going to be many other black magics, but okay, this will be later. Good. So this lecture is dedicated to, I'm trying to give you a general, not a general outlook, because this is something to do in the last lecture of the semester. I'm trying to give you some outlook, a preliminary outlook. Yes?
Can you tell about the name of the second way to solve the unsolvable
You can ask in Hebrew, by the way. I will...
השיטה השנייה, איך קמה?
Numerical. Numerics.
לא השיטה הראשונה.
Perturbation theory. I will say this word so many times that... So the problem is, once you start writing non-solvable not solvable equation on the blackboard and start doing gymnastics, right? Then there is a chance that people will not see the forest but only the trees. So in an attempt to give you some preview of the forest, I'm starting with relatively simple example, and then we will, in the next lectures, we will continue to deal with more complicated situations. So, essentially, as I said, what we want to do is to do perturbation theory. What is perturbation theory? We have something that let us call something HP, not a computer manufacturer, but hard problem. Hard problem. By the way, I've forgotten to say, this course is based on the book of Bender and Orszag, the yellow book, holy yellow book of Bender and Orszag, asymptotic methods for physicists and engineers, or something like that. One of the most valuable books in terms of useful information per centimeter squared. Very recommended to anybody on earth to read before you get asleep, or as the method to get asleep. But an extremely interesting and important book. There is also a series of lectures of Karel Bender on YouTube that I used a little bit when preparing this course, and also very recommended to any of you. This is something that I forgot to mention. Okay.
Maybe write the name of the book.
Okay. So the first one is Karel Bender. That's an easy one, right? And Orszag is something like that. but these are the two authors, and the name of the book is Bender and Ozag, Advanced Mathematical Methods for Scientists and Engineers. It's supposed to be the first part of the book, but they never published the second. Or maybe this is the second and they never published the first. Something like that. Okay. So we start with a hard problem. Let's put a hard problem, a concrete hard problem. Here is the quintic equation. This is supposed to be a hard problem. Okay? And I don't know how to solve it. Good. What's next? So nowadays we have all these, Mathematica and Maple and all programs that give you solutions, so you can solve it numerically. You can solve it numerically, and I will tell you that the answer is 0.75488. This is the solution for this equation. Of course, it continues. Okay? And the question is, okay, so this is a numerical solution, as I told you. You can solve everything numerically. But now you may wonder, maybe if I will put here, instead of 1, I will put 1.1 or 0.9, what I will get? Maybe I will get 100. I don't know. Okay. So I want to get some analytical handle on this problem. Okay, that's our goal. So here is what we are doing. We will introduce the physicist's best friend, epsilon, which is a small thing. Right? So instead of that, I will write x to the 5 plus epsilon x equals 1. Okay. Now I can solve the problem for epsilon goes to 0. What will be the answer? 1. Is that the only answer? No, because the basic theorem of algebra tells us that if it's a fifth order equation, it has 5 solutions. So we know that it will be 1 and square root of, you know what the 5 answers, right? They are in the complex plane. But one of the answers will be 1. Okay. Now, let me show you what I'm doing, and then we will return and explain to ourselves what we did. Right? So, what I'm doing, I assume that x may be written as sum from n equals 0 to infinity of an epsilon to the power of. Okay? Let us see how much we can, and since epsilon is small, the higher powers of epsilon are assumed to be smaller and smaller and smaller, and maybe, hopefully, we will be able to grab something from the lower powers of epsilon. Okay? So, I'm going to start. So, okay. So, let's, for the moment, okay. First of all, what is A0? So, this is A0 plus A1 epsilon plus A2 epsilon squared plus A3 epsilon cubed plus blah 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 blah. Okay? You are, you're still with me, right? Okay. Now, What is A naught? Okay, let's go back to here. So I'm writing x to the 5. I'm writing it as, okay, you can very easily see that A naught is 1. Right, but okay, let's write it like that. Let's call this S. Okay, and what do I want to do? Okay, and let's assume for the moment that A naught is 1. I didn't show that, but I will show you it in a moment, right? So what I have here is 1. Okay, so x to the 5 is 1 plus s to the 5th power. Okay, and this is because okay, A naught is what you have when epsilon equals 0. If epsilon equals 0, I have x to the 5 equals 1, and the answer is 1. Okay. Now, I have a 1 plus s to the power 5. Anybody remember how to expand that? Right? This is a binomial. Yes? Okay. So this is 1 plus 5s plus 10s squared plus 10s cubed plus 5s to the 4 plus s to the 5. Right? Pascal triangle. Okay? But we will be interested only in this part. Okay? Now, so how this looks like, I have 1 plus 5 A1 epsilon plus 5 A2 epsilon squared plus 5 A3 epsilon cubed. You see? This is it. And then we have plus something to the 4 power and so on that I don't want. I want to confine myself to epsilon to the power of 3. Right? Now, let's continue. Plus 10s squared. But now you have to help me, right? 10s squared. I have 10 A1 squared epsilon squared. Okay? Plus 20 A1 A2 epsilon cubed, right? And all the other powers are higher than cubed. You see? Next, I have 10s cubed, but from the 10s cubed, all I need is 10 A1 cubed epsilon cubed. Okay? Now, so I have x to the 5 that I expanded here up to 3rd order in epsilon. I expanded it. And I have epsilon x. Now, let's start collecting terms in orders of epsilon, consecutive orders of epsilon. Okay? One by one. So we will start with epsilon to the power of 0. Epsilon to the power of 0 is 1. And what is this equation? This equation, right? If I collect only 0th power of epsilon.
1
What?
is equal to 1.
Yes, exactly. 1 equals to 1. Okay, so this is another proof that A0 is 1. Okay? Are you with me? Good. Epsilon to the power of 1. Oh, wait. Okay. 1 equals to 1. So we assume that A0 is 1. And to this approximation, our x is 1. right? Because x is now 1. We neglected all these terms. So to the zeroth order approximation, x is 1. The truth is x 0.75 blah blah blah. Good. Next. First order in epsilon. What we are doing? I collect only terms that are first order in epsilon. So in the x to the fifth, what I have which is first order in epsilon?
5a1.
What?
5a1.
5a1. Only this. Okay? 5a1 plus what?
1.
In x, what I have that is first order in epsilon? 1. Plus 1 equals what?
0.
I have here 0. No, don't count the 1 twice. Right? The 1 played its role here, in the right hand side. It will not appear again. 0. So, what is our approximation for A1? Not approximation. What is A1? Minus 1/5. You see? Okay? So, what is my approximation to x? Let me do it like that. This is my approximation to x. And this will be, this will be my approximation to x in a moment, right? This is 1, right? Now, my approximation to x, the red approximation, the first order in epsilon, is, sorry, I will do it the other way around. This will be x of epsilon, and this will be x. In a moment you will see what I mean. So A1 is minus 1/5. So my approximation for x is 1 minus epsilon over 5. Okay? Now, this equation, which I'm interested in, what is the value of epsilon? 1. So if I put epsilon equals 1, I'm getting 1 minus 1/5. And 1 minus 1/5 is 0.8. So, nice. We have made an advance, right? We did something. We are closer to the right answer. Good. Next. What is the next line? Epsilon to the power of 2. Can you help me?
5a2.
Who is playing the epsilon to the power of 2 here? This one and that one. Okay? So I have 5a1 plus 10 a1 squared plus, now I have this epsilon times x, where this is x,
Plus 5a1.
plus a1, no, epsilon times x, wait,
Yes,
Plus
A1.
a1.
plus a, no, so everything depends on a1. This is
No,
impossible.
it's A2 on the start.
This one, this is a2.
Yeah, this
This is a2. Okay, good. Plus what?
A1.
Plus a1. This is equals 0. So we find out that what is a2? Let's see. 10a1 squared. A1 is minus 1/5. So 10a1 squared is 10 over 25. And now I have minus 1/5, which is 5 over 25, right? So, and I have here 5a2 plus that. So altogether, we find that a2 is 1 over 25, right? Because this is 5 over 25. We take it to the other side, to here, so it's minus 5 over 25, so it's minus. and divide by 5. Right? 1 over 25 is 0.004. So our approximation now in this stage is that x of epsilon is 1 minus epsilon over 5 minus epsilon squared over 25. And if we plug epsilon equals 1, we have to subtract 0.04 from 0.8 and we get 0.76. Look at the answer. Not bad. Yes.
Where did the third term come from? The A1?
Which one? The A1?
Yeah.
From epsilon times x, and I am collecting all terms that are order epsilon squared. So this is x, right? And epsilon times x contains A1 epsilon squared. So that's A1. Okay? And yes.
If I want to get the other solution of the equation, so I can just use the other solution to the epsilon equal 0 case?
Put your question on hold for a moment, please. And just to be complete, let's speak about epsilon to the 3. Okay? So what we are going to get? We are going to get 5 A3. You see? This one plus this one plus that one. Right? 5 is 3. Let's write it here. Right? We have five A3, which is this one, plus 20 A1 A2, plus 10 A1 cubed, plus A2 from here. Right? Plus A2. All this equals to 0. So A2 is minus 1 over 25. Right? A1 is minus 1/5. Cubed of this is 1 over 125. Right? With a minus. So I have 10 over 125 with a minus. So we can write this one as 5 over 125. Just to have a common denominator. And this thing is 20 times A1 times A2. A1 was minus 5th, A2 was minus 1 over 25. So again we have 125. And this is minus, so they are plus, and I have here 20. Right? And here I have 5A3 plus this equals 0. So 20 minus 10 minus 5, so I have 5 over 125. The 5 cancels out. And I have A3. So what I will get is A3 is minus, I guess, 1 over 125. So we will get the approximation of is 1 minus epsilon over 5 minus epsilon squared over 25 minus epsilon cubed over 125, and 1 over 125, okay, you have a calculator, it will improve a little bit, right? How much is 0.76 minus 1 over 125? Any answer?
0.752.
Oh, 0.752. Which is, by the way, it's a little bit. For example, would you like to guess what will be the next term?
A positive.
A1 was minus 5th, minus 1 over 25, and minus 1 over 125.
1 over 1
5
over
to the 4,
1 over 6 to 5.
1 over 5 to the 4. Good. This is what a good physicist is supposed to do and supposed to continue the calculation. In this specific case, the next term is 0. And then they become positive in order to compensate for the over, okay? So this is the perturbation theory. Okay? Now, what we did. Let's look back and see what exactly after playing with numbers, what exactly we did. We started with this equation. We didn't know what to do. Okay? We introduced epsilon. Why? Because we have no other choice. We have chosen the epsilon in such a way that if epsilon is 0, we can solve the equation. Right? This was a trick. We put epsilon in a place where if it is 0, we can solve the equation. Okay? So when epsilon is 0, we have a solution, and the solution is A0, which is 1. Then we assumed this expansion. And we have calculated the epsilons term by term and got an infinite series from which we have calculated the first 3 terms. Okay? So if we continue this, if I will have infinite lecture, I will continue it and we calculate A4 and A5 and A6 and A127, and I will get all these, right? So we took hard problem, we introduced epsilon. From this, we arrived at an infinite series from n is 0 to infinity of an epsilon to the power of n, right? And now, what we have to do, suppose I have this series. What I have to do? What's the next step?
Substitute.
What?
Substitute to the equation.
Substitute. So to get the equation, the equation I am interested in, I would like to substitute epsilon equals, in this case, epsilon equals 1. Right? Of course, I may be interested in a question where I have 2 here, or 1/2 here, or whatever. Right? But for this specific question, for which the answer is given by this, numerically, I have to substitute epsilon equals 1. Right? You understand it. So this is the general scheme of perturbation theory.
Can I ask a question?
Wait. May I end the sentence? Take an equation that you don't know how to solve. Plug epsilon in whatever place you like, right? In such a way, I mean, it is so advised that you plug the epsilon in a place that without at epsilon goes to 0, it is solvable. Then expand the result in powers of epsilon, calculate the whole series, maybe you can do it analytically, I don't know, and then plug the calculate the series, and then plug epsilon back to the epsilon equals 1 or whatever you like, 1/2, 2, and sum up the series. So it's a 3-step program. Put an epsilon, calculate the series, plug epsilon, plug the right value of epsilon. Okay? That's I want you to understand. So take hard problem, put an epsilon, calculate the series, and plug epsilon, the value of epsilon you are interested in. Yes. Okay, now questions.
In this particular case, we also can put epsilon in the right-hand side of the equation.
Thank you very much for that. I mean, this is a great question. You know what a great question is? The question that the lecturer is pretending to, I mean, is planned to speak about in a minute. Yes. This is a great question.
Okay.
Yes.
לא.
יש עוד משוואות מהצורות האחרות שזה יכול לעזור לנו השיטה? כי זה או רק עבור x בחזקה גבוהה פלוס משהו עם x שווה ל...
Okay, the question is, are there any other equations that in which this program may help us? The answer is yes, with capital S and capital Y and capital E, meaning that physics is meaningless without this program. Why physics is meaningless? Because you know that the ancient Greece, for what purposes the ancient Greek implement mathematics? It's very interesting. They've implemented mathematics only for two purposes.
Structures.
I mean, not geometry, but geometry they also, did for in order to divide the land. But algebra, mathematics, in the sense we are speaking about, they're implemented into two topics. What are the two topics?
Navigation.
What?
Navigation.
I mean, calculating the orbits of the planets, right? The cosmology, the astronomy, say, and since Pythagoras, music. Okay? Why they implemented mathematics only in for these two topics? Because they were smart. And they say this as follows. Mathematics is dealing with perfect objects. You are speaking about a cylinder. There is no cylinder in the world, right? When you build a cylinder, it always have, some jiggling and things on the atomic level, right? The tire of your car is not a cylinder by any means, okay? So in order to solve something, you want it, so they had the feeling that mathematics is, you should use mathematics only for perfect objects. And these perfect objects were the planets that are made of ether, which is another, another material, a perfect material, and are going round and round and round without, any tricks and shticks, and music, which is of course reflecting also some kind of eternal and perfect truth, but it's not, it's a spiritual thing, yeah. And on the other hand, they didn't want to implement mathematics for the trajectory of this pen when I throw it, because they said, there are so many imperfections, and I can throw it in so many angles and so on. There is no way to use mathematics for it. And the reason why we have made such an advance in implementing mathematics to natural sciences, the guy who we should thank was Galileo. Galileo was the first to implement mathematics to natural science, to study a pendulum, to study, inclined planes, and so on. He was the first to do that, and he was asked by his contemporaries, what is your license to do that? You are writing an equation for a pendulum, assuming that, it's a point mass, but it's not a point mass, and you assume that the rope is perfectly rigid, but it's not perfectly rigid. So what is going on? What is the justification to use mathematics that assume perfect objects for things that are not perfect? What was the answer of Galileo? Of course he didn't answer because he didn't know the answer, but he saw that it's working. It is working. So he continued. Okay? But if he was, equipped with the right mathematical knowledge, this was his answer, right? That, okay, the tire of my car is not a cylinder, but it is close enough to a cylinder in order for me to neglect to first order the differences between the tire of the car and the cylinder. Now, when I plan a car, now you want to know what will be, what are the deviations from my solution? Okay, so there is some parameter epsilon that stands for the difference between my tire of the car and a cylinder, and I will calculate the trajectory of my of the car or of the tire using perturbation theory. Right? That's the only. I want to. It's not history, right? That's the only. way to make physics meaningful. Right? That's the only venue that allows us to really implement mathematics to nature. Because mathematics is for perfect things, nature is imperfect, and what physicists are doing is to neglect, right? הפיזיקה מתחילה בנניח, ממשיכה בנזניח ונגמרת בנוכיח, כן? So this is what we are doing. We neglect many things, and how do we know that they will not change, what we have neglected will not change completely the answer? We can control it using perturbation theory. So perturbation theory, this is again a great a great misleading point in first degree in physics, that at least when I ended up my first degree, I got the feeling that perturbation theory is a branch of quantum mechanics, because this is the only place where it is introduced to you. No, perturbation theory is a justification for doing physics. Now, any other question? Yes.
First of all, if you said for example that you can have coefficients of 2 for the x and such things.
Yes.
What to do if the series diverge?
Thank you very much. Actually, the only reason why I say now, is there another question? I don't want to waste time, but I hope that somebody will ask this question. Right? So Mr. Nimrod pointed out a fatal problem in our program. Right? What is the fatal problem? We said, okay, we don't know how to solve the problem. We will put epsilon. We will calculate infinite number of coefficients. Maybe we know how to do that. And then we plug epsilon goes to 1 or 2 or whatever. So Mr. Nimrod is asking us, here we did a very strong assumption. What was the assumption? The assumption is that the sum over an, suppose I would like to put epsilon equals 1, for example, this sum converges to some number. Maybe this series is diverging. Right? This is what worried Nimrod. Answer. The problem is much more than what you think. All the important perturbation theories in physics are divergent. Right? So the answer is infinite, no matter what. Okay? And what I hope to teach you during the semester is how to deal with that, and how to extract the required information from diverging series, which is, scary, but this is what we are going to do. And it turns out, again, as I told you, that it's much easier than to extract information from converging series. Okay, so the diverging series are one of our best friends. I'm going to show you why, but this is for the future. By the way, just something that I've forgotten to say, not connected to anything. What allows me to do this order by order, requiring all terms that are proportional to epsilon to sum up to 0, all terms that are proportional to epsilon squared, term by term, this is the uniqueness of Taylor series. Right? Because of the uniqueness of Taylor series, I am allowed to do the calculation term by term. There is no way that the epsilon cubed term will compensate for the epsilon squared term. Good.
That is linear algebra, right? The polynomials are linearly independent. That's what you meant.
I meant that Taylor series is unique. There are no, if two Taylor series are describing the same functions, then their coefficient A1, A2, A3 are equal to each other one by one, which is what I actually did here. Okay, now, what about this specific problem? So, some good people made an effort, and figure out, you see that if I'm asking whether or not this series converge or not, it depends on epsilon. If I'm starting for epsilon smaller than 1, then at least the epsilon to the power of n is decreasing exponentially. So if the a_n's are not going to increase exponentially, I will be on the safe side, right? Whereas if epsilon is smaller than 1, they will increase exponentially, right? And then I want the a_n's to go down faster than the corresponding exponent. Okay? So in this story, the radius of convergence of this series for this specific problem, the radius of convergence is 1.649, right? Which implies that.
So for 1.7, I can't solve this like that?
Right. So if we have, right, this is the real part of epsilon, and this is the imaginary part of epsilon, right? The answer will converge for every point in the circle that this point is of its radius is 1.649. Right? So here is the radius of convergence of this specific problem. Good. Okay, so this implies that if we want it for epsilon equals 2, this series will converge. Will diverge. Sorry. Is that a problem? A substantial part of this course will be devoted to convince you that this is even better. Fine. Next. Our next thing we would like to do is, now let's try to do something else. I'm still looking at the same problem, but who suggested this? You, I guess.
No, I suggested that the right hand part.
To put the epsilon here?
Yes.
But this is 1. Okay, you can do that. Yeah, you can do that. Fine. But let's put it here. Just for fun. Right? And, okay, so if epsilon is 0, what is x? 1. So a0 is 1. Now, what's happened when I'm doing the calculation? Okay, a0 is 1. Next, what will be the next correction? What will be if I'm now collecting things to the power of epsilon? Note that I can use the same expansion, but now the epsilon is the coefficient of this monster, not of this one. Okay? So now we are collecting terms that are order epsilon to the power of 1. I have epsilon times x to the 5. So I should take all these and multiply it by epsilon. To first order of epsilon, what do I get?
Epsilon.
1. 1 is the only coefficient of epsilon. Right? We have epsilon here and it multiplies all this. Right? So 1 plus x. So plus a1 is 0. You see? You see where it comes from? Okay? Which implies that a1 is what? Minus 1. So we are to this level we assume that x of epsilon is 1 minus epsilon, and if epsilon is 1, x is 0. Quite bad. The zeroth order, the second order is much worse than the first order. Right? The first order gave us 0.8. This is the right answer. the second order gave us 0. Okay, let's figure out what's happened with the second order. Maybe it will save us, right? So what's happened about what about epsilon squared?
5.1
I have 5a1
plus 5a.
Plus 10a1 squared.
No, wait.
No, 5a1, that's it.
Plus A2.
Plus a2
Equals
equals 0, right? Okay, and this implies that a2 is 5, right? Which means that x of epsilon is 1 minus epsilon plus 5 epsilon squared. And if I plug epsilon equals 1, I have 1 minus 1 plus 5. So the answer is 5.
We just keep
So
getting
how do we
away.
know- So how do we know where to plug it?
What?
So how do we know where to plug the epsilon? If you
Wait. This is, I'm trying to prepare you to the material of the course, right? So next, what about epsilon cubed? I should take the 5a2 plus 10a1 squared plus a3 equals 0. So what is a3? 5a2 is 25. a1 squared is 1. So I have 5 plus 10. So it's 35. 35. So a3 is minus 35. Okay? So our approximation now is 1 minus epsilon plus 5 epsilon squared minus 35 epsilon cubed. And if we plug epsilon equals 1, we have 5 here and we have to subtract 35. So we have now 1 minus 30. So you see what's happened, right? This is a crazy Taylor series. Do you believe that this will converge? No. All the chances it will be oscillate with bigger and bigger oscillations to infinity, and we will get garbage for it. As I told you, this is the best situation, but we will have to prepare ourselves to deal with it. Okay? Is there any chance that it will converge for any epsilon? Right? Maybe if epsilon was 0.1, right? Then it will look much better because now I have here 0.1 minus 0.1, right? It's 0.9, and this will be 1 minus 0.1, and here I have 5 times 0.001, which is very small, and so on and so forth, right? So the coefficients are growing larger, but the epsilon, if really small, will be may give us a hope for convergence. In fact, again, some mathematicians worked on it, and figured out that, where is this number written here? I 0.00819. So the radius of convergence is 0.00819 something. 0819 something like that.
た OO
0.08192. Right? This is the radius of convergence of this series.
So it depends on place of epsilon.
Okay. So so as you have seen now, we had tried our luck with two types of perturbation theories. Right? One of them was we put the epsilon here as opposed to x to the fifth plus epsilon x equals 1. This was the first series that we tried, and this is the second one. As you see, this one was quite nice, while this one was very good. Okay. Why? Okay. Can we know in advance that this will be the answer? To some extent, yes. And by the way, just as a remark that I don't want to elaborate on, there are other ways. For example, we can do perturbation theory by writing x to the 1 plus epsilon plus x equals 1 and plug epsilon equals 4. Right? When epsilon equals 0, you see that x is 1/2, and then we can expand it. But it's more elaborate. I just mention it. I'm not. This is not in the material for the examination. Okay. So what is the reason for the general success of this to the general failure of this? The reason is that here we put epsilon at the coefficient of the highest order term. That's a problem. When epsilon is in the coefficient of the highest order term, you know that if this term, when epsilon equals 0, how many solutions this equation have? 1. If epsilon is not 0, it will have 5 solutions. So there are 4 solutions that are sort of invoking from nowhere in the jump from epsilon goes to 0 to epsilon goes to epsilon, right? To any number, right? And this is an indication for the thickness of the perturbation theory, right? Every time your small parameter, now let's assume that epsilon is really small, right? Every time your small parameter is in the coefficient of the highest power or the highest derivative, right? If you have a differential equation, when the small parameter is in the coefficient of the higher derivative, you get a disaster. That's and usually the radius of convergence of this theory, I told you that here the radius of convergence 1.00 something, it disappeared. Usually the radius of convergence is, in physics, physical problems, is 0. Strictly 0. Yes. Okay. I have a great example, but I have no time. So I'm continue, and if time allow, I will tell you something about it. Good. So, but almost everywhere in physics, we have the epsilon here, not here.
So if I will plug epsilon to the 5 next to x to the 5.
It doesn't matter. I mean, because the point is that epsilon, the problem changes dramatically when you move from epsilon is 0 to epsilon is epsilon.
Okay.
You assume that you say that everywhere in physics you put the epsilon in the highest order because of the neglected because regularly we work
It
with
is so
small
happen
numbers.
that
We work with small numbers, so the highest order is at the neglectable one.
Yeah. It's
Right? If I understand correctly.
again. What is your question?
My question is the reason you say that we put that usually we put the epsilon on the highest order.
Not we put. Unfortunately, God puts. So the point is that in most of the physical problems, you have to identify a small parameter, right, in order to neglect something. A really small parameter. Here epsilon was only an instrument. It did not reflect anything. It is 1, but we put it as a small parameter. But in almost all cases in physics, there is a small parameter, hopefully, right? And the point is that this small parameter is usually in the coefficient of the highest derivative. Classical example, if you want, Schrödinger equation. What's a small parameter? H bar, right? If you deal with macroscopic objects, you know that you should retrieve Newtonian mechanics, hopefully, right? But in Schrödinger equation, the H bar is in the coefficient of the second derivative. So the H bar is a small parameter, but it comes in the coefficient of the highest derivative. And that's why you can't get rid of it. That's why getting Newtonian mechanics from Schrödinger equation is a very, very, very difficult problem. Okay, next. So now let us define two concepts. It's not proof, it's a definition, right? First of all, I have two functions, f of x and g of x, and this definition is f of x is asymptotic to g of x at the limit x goes to x. Just x. What does it mean? It means that at the limit x goes to x naught, f of x over g of x is going to 1. Is 1. Yes.
It's like Bessel functions with cosinus and sinus.
Yes. Yes. Right? So for example, examples, is e of x asymptotic to 1 at x goes to 0?
Yes.
Yes. Okay? You see? Another question. Is x cubed asymptotic to x cubed plus x to the 4 at x goes to 0?
Yeah.
Yes. You see? That's fine. Is x cubed asymptotic to 0 at x goes to 0?
No. And divide by 0.
No. Yes. Because right? Wrong. Well, nothing can be asymptotic to 0 because of the definition. See? Okay. Did you grab the definition of an asymptotic relationship? Right?
So it's like the first meaningful term.
Something like that. Yes, yes, yes. So for example, if you want a historical example, people were interested, why? I'm wasting time. Okay. People were interested in the number of prime numbers, right? You start with the prime numbers. In the first 10 numbers, you have primes are 2, 3, 7, and that's it? 5, yes. 2, 3, 7, and 5. So we have 4 prime numbers, right? But as the numbers increase, the density of the prime number decreases. Why? Because it's very difficult to be a prime number when you have so many optional numbers that can divide it, right? So the question is, what is what they call pi of n? Pi of n is the number of prime numbers smaller than n. The number of prime numbers smaller than n. You understand the question? right? If you really count, if you really plot pi of n as a function of n, you have many steps here, right? Each time you have a prime number, it goes up by 1, right? But if you look at this curve from a distance, you may think that it's, and the question is, how this function is looking like. Looks like. Okay? And Gauss suggested that pi of n is given by is Li of n, which is the integral from 1 to n of dx over ln x. This was and it's more or less, at large numbers, it goes like n over ln n. This is Gauss's estimate for the number of prime numbers up to n. Right? And so it was shown, the mathematicians have managed to prove that as n goes to infinity, note that there is no meaning, it's meaningless to say that f is asymptotic to g, only that f is asymptotic to g at the limit of something go to something, right? So in the limit n goes to infinity, pi of n is asymptotic to zero. This has been proven by Adamar at, it's also an interesting story, but anyhow, it was proven at the end of the 19th century, one of the greatest victories of mathematics to show that, right? Now, but this is just an asymptotic relationship, which implies that maybe pi of n is actually equal to Li of n plus, say, n to the power of 0.99, right? Note that this will be negligible with respect to n over ln n, as n goes to infinity. Right? So this may be also true. Right? We don't know. What the mathematicians know is that in the best case, the difference between pi of n and Li of n is order square root of n ln n. Cannot be smaller than that. Right? It cannot be smaller than that. And to prove that is the holy grail of mathematics, because this is actually to prove that the what's the name?
Zeta function.
Ma?
Is the zeta function?
Yes, the Riemann hypothesis. This is to prove that is to prove Riemann hypothesis. So it's still an open problem, and if you can do something about that, then please get out as fast as you can from this course and spend your time on. Anyhow, okay. I'm wasting time. So the next relationship is f of x is negligible to g of x. So this does not mean much smaller than, right? As physicists are usually implementing this sign, because there is no actual definition to much smaller than. Is 3 much smaller than 4? I don't know. Right? But here, you have to read it in this course, you have to read this sign as f of x is negligible with respect to g of x as x goes to x naught, which implies that as x goes to x naught, f of x over g of x is 0. right? So, for example, x squared is negligible with respect to x at x goes to 0. But just to give you a warning, this is also true. Wait. So, x squared is say it another way. X is negligible with respect to minus x squared as x goes to infinity. You see? Although minus x squared is clearly smaller than x. I'm not saying that it is smaller. I'm saying that it is negligible with respect to. You see what I mean? Okay. By implementing this definition, we can start get a handle on equations like that. How do we do that? Very important technique that we are going to use again and again and again during this course, which is dominant balance. What dominant balance is? What dominant balance is? So first of all, we are going to write epsilon x to the 5 plus x equals 1. Right? This is the equation. And we start by staring at this and having our heads and think what is going on here. At the limit, okay, now I want to study this equation. At the limit, epsilon goes to 0. So now epsilon goes to 0 is not, as before, just a trick, but I want to know what this equation is doing at epsilon goes to 0. Now, here is a trick that is called dominant balance. Dominant balance. Dominant balance means doing the following argumentation. We have three terms here. It is not reasonable that when epsilon goes to 0, all these three terms are of equal importance. I expect one of them to be negligible with respect to the two others. Right? So I will replace this equation by the following equation. This is all. At epsilon goes to 0. And now I'm asking, at epsilon goes to 0, what is okay. It cannot be the case that both this and this are negligible. Why? Because then I cannot satisfy the equation. To satisfy the equation, two terms have to balance each other. So we have three possibilities. You see? The three possibilities are epsilon x to the 5 is asymptotic to 1 and x is negligible, or x is asymptotic to 1 and epsilon x to the 5 is negligible, or epsilon x to the 5 is asymptotic to minus x and 1 is negligible.
Why does one of them have to be negligible?
Because it should be a miracle that all three will be the same, of the same order of magnitude as epsilon goes to 0. Right? Sometimes it happens, but shit happens, but we will neglect it. We are trying to neglect it, right? You see? So these are the three options. And the question is how to Okay, now the question is, which of them is self-consistent? That's a trick.
When you are, for example, saying x is asymptotic to 1, in which x is function f of x equal x?
As epsilon goes to 0, x will go to...
No, but I mean, when you said the definition, you said that about f of x is asymptotic to g at x at x naught.
Yes. Okay,
What happens here?
Give me
It's in every...
other 10 seconds.
Okay.
Right? Let's start with whom I would like to start. Let's start with this one, right? If this is true, then so one possibility is x equals 0 that I will not take into account, and another possibility is that x to the 4 times epsilon is 1, as epsilon goes to 0, is minus 1. So x to the 4 is minus 1 over epsilon. So x is going like minus 1 over epsilon to the quarter. Sorry. Minus 1 to the 1 quarter over epsilon to the quarter. Is that consistent? What does it mean, is that consistent? I am going back to my original equation and I will plug it here. Right? So here I have epsilon x to the 5. X to the 5 is minus 1 to the 5th fourth divided by epsilon to the 5 fourth. Right? Plus x, what will be x?
Minus 1 over.
X will be, here it is, right? Okay? X will be minus 1 over 1/4 divided by epsilon to the power of 1/4, right? And this should be equivalent to asymptotic to 1. Now, is that self-consistent? What I did, I have neglected this, right? Is it true that this is much smaller than that? As epsilon goes to 0.
No.
Is it true that this is much smaller than that?
No, you get it the 1.
Wait. Sorry, I did a mistake. What wait. Okay, sorry. I think it's okay, but let's start with another option, right? I wanted to start with here I neglected the 1.
Yeah.
Okay. Let me start with this option. Okay. So x is 1. So what I've neglected is epsilon x to the 5th, which is simply epsilon, right? So I neglected epsilon with respect to 1. Is that consistent?
Yes.
Yes. So this is and what it gave us, of course, is the first term in the expansion that we got with when we put the epsilon here. Right? Good. What about this option? If epsilon x to the 5th is going like 1, it implies that x is going like 1 over epsilon to the power of 1/5. Okay? Is this consistent? Is that consistent? No. Why it is not consistent?
It goes more than 1.
Negligible.
Yes, because as epsilon goes to 0, this diverges, and this is 1. So it cannot be that this balances that, because this is much larger than both. Right? So this is inconsistent. and we have this one that gave us one solution, and this one that gave us another 4 solutions. Okay? Now, the other 4 solutions, and now if we want to check for consistency, we have x is going like 1 over epsilon. Okay. So it's the 1. Here I neglected the 1. This is okay. This was my mistake. Here I've neglected the 1. Clearly, if epsilon x to the 5, you see this term is going like what? Like 1 over epsilon to the 1/4. This one goes like 1 over epsilon to the 1/4, and this one is 1. As epsilon goes to 0, these 2 terms are much larger than this one. So this is self-consistent, right? So this one is self-consistent, this one is self-consistent, and this one is not self-consistent. And now, here is the trick. So now we can write the equation like that, you see? And you see what's happened. Okay, or, no. Now I can continue. If I want to develop a perturbation theory, what should I do? I have to define, okay, I will define x equals y divided by epsilon to the power of 1/4. Why that? Because then, if x is going like 1 over epsilon to the 1/4, then y will stay order 1. This is the trick, right? We know what x is doing when epsilon goes to 0, and now we write it in a way that will stay order 1, and then we plug it here. So what I have is epsilon times y to the 5 divided by epsilon to the 5/4 plus y divided by epsilon to the 1/4 equals 1. Now, epsilon divided by epsilon to the 5/4 is epsilon to the 1/4. So this gives me y to the 5 plus y equals epsilon. And now I can continue the analysis. Now I have a completely, perfectly kosher, not kosher.
Not an epsilon.
Epsilon to the 1 over.
To the 1/4. Sorry. To the 1/4. Yes. So this is a small parameter, and now the small parameter moved to here, which is what you want me to do in the first place. And you can very easily write a perturbation theory by plugging y equals to the sum from n equals 0 to infinity of an epsilon to the power of n over 4. You see, that's an important thing. Not epsilon to the power of n. Now it comes with a broken power of n because of that. And from now on, it's a standard perturbation theory. Right? So this allows us to do standard perturbation theory after doing this change of variables. For what? For the 4 roots. I mean, you remember that this equation has 5 roots. But if I am taking epsilon to 0, I have only 1. Okay? The 1 is here. This is the 1 root, which is x equals 1. Right? And here you get the 4 roots that what's happened when epsilon goes to 0? How do they disappear? We know that as epsilon goes to 0, we have, at epsilon equals 0, we have 1 root. But when epsilon is finite, we have 5 roots. What these roots are doing, if this is a complex epsilon plane, this is the real epsilon, and this is the imaginary part of epsilon, right? You can figure out that these 4 roots here are going like that, are going to infinity. Right? They are not going to 0 or something, they are going to infinity. And this is why this is a singular problem. You see why it's singular? When epsilon goes to 0, you have only 1 root. for any finite value of epsilon, you have 5 roots. One of them is, okay, is around 1, is here, very close to this one, to here, but all the others are blowing up to infinity as epsilon goes to 0. Right? And, okay, so unfortunately, I've exhausted my time and I can't give you the physical example that I wanted to show you, but these are the, this is the essence of the story, and next week we are going to, now the first 2 תרגולים will be, we'll try to, you know, to ליישר קו, about things that you are supposed to learn, you know, differential equations of all kinds and so on. So there is some sort of a detachment between me and the instructor for the first 2 meetings, but later we will, I hope, converge together. Thank you very much.
Actually, today's tutorial will be just a refresh on things from general course in OD. Actually, classic course in OD. Okay, so we will start from 0 and progress from there. We will progress very fast because you already know most of the stuff. Okay, so homogeneous. Homogeneous. Just checking.
התרגול עלה למודל?
Yes, everything is on Moodle. Homework and the submission of the homework. The submission will be to next week, Wednesday next week. Every week I am supposed to upload new homework, so we will see. If there is no need for another homework, I will not upload, and then maybe I will give the homework before a little bit. I will make it a little bit bigger, so it will take a little bit of more time. They're not supposed to take you that long. Tell me if I did something wrong and gave you something that is very long. I don't want to make it hard for you. Maybe there will be hard questions, but not. Okay, we will see. But I don't want it to take all of you. Okay, so homogeneous ODE. What is ODE? Someone know?
Ordinary differential equation.
Yeah, right. Ordinary differential equation. So what is? Okay, maybe we need to add that word, linear. Linear homogeneous ODE. Usually when I'm saying ODE, I will mean linear. If it's not linear, usually I will say it's non-linear. Okay? Just make some notation. Okay, so what is linear homogeneous ODE? Let's write nth order. It's just a sum of function coefficients, okay, from n equal to 0 to, let's say, capital N, y. That is how I will note the derivative, okay? That's how we will write the derivative. that is the nth derivative. What is doing zero derivatives?
Just the function itself.
Doing nothing. The zero derivative of y is just y. The one derivative is the first derivative. I mean, y1x is the first derivative, equal to 0. Just
I think you meant n, small n on the top of the sum, because you were talking about the nth order.
Okay, maybe write it. It's a little bit different notation than what I wrote in the tutorial, but I don't want to be a robot and write exact. It's just letters, okay? Note that the solution y equals 0 is a solution to the homogeneous, linear homogeneous ODE, right? That is the what? That is the most basic stuff of the first thing you saw in ODE course. Now, non-homogeneous, I will just write non is just same thing, same, but now we have another function g of x that is differentiable at all of the domain. Okay? We maybe sometimes we look at the domain of a to b, and maybe sometimes 0 to infinity or minus infinity to 0, and maybe sometimes all of the real axis. Okay? I'm writing it with capital R, with the fat R, just fancy math. I mean minus infinity to infinity. Okay? Oh, by the way, if something is if I say something that maybe not correct, I can have some mistakes in calculation, just let me know. I don't think so. I checked myself twice, but it can be happen that the first time I'm doing the exercises I wrote and doing this tutorial, I wrote the tutorials especially to this year. I have once a week meeting with Snab and we decide what will be in the tutorial. Okay? And if I'm not clear, you can ask questions, of course. Okay. Boundary conditions. What are the most famous boundary conditions? Let's do this section in what are the most the well-known boundary conditions?
Periodic boundary.
What you say? Yeah, there's Plan, Neumann, all of those stuff. For example, I will just give y of a equal to a, capital A, right? And y tag of b equal to b. Maybe we have some limit. That means y at infinity equal to 0. Usually you see that in, for example, electromagnetism, right? If y is the potential and the system is just one point that has q charge at infinity, let's look on one dimension, the potential will be 0. Boundary condition usually is where the physics in the system evolves. It actually not evolves. The right word will be איך אני אומר לידי ביטוי? It's how the physics will
come to be.
Yeah, okay, it works. Sorry, I'm not a native English speaker, so I'm sorry.
Me too.
Okay, so we will be fine. That is my first time I do tutorial in English, so yeah. Okay, let's do it also. What is the number of solution to nth order differential equation? An homogeneous one and one actually for non-homogeneous we put another. Okay. Number that notes the word number of solution. Right. So okay. Homogeneous case for nth order OD, we have n independent solutions. Okay? Everyone knew this? Is it new to anyone? No? Okay. What it means to be independent?
That the Wronskian is different.
It's different from 0 at one point. Or equivalent, it's dependent if for all points at the domain it's equal to 0. Right? By the way, every function in this tutorial will be differentiable. Don't even ask me that. Okay? If there is any mathematician here that want to talk about non-differentiable function, they can come to me after and we can have a discussion on non-differentiable. Okay. So the Wronskian, everyone is familiar with the Wronskian or they need a reminder? Okay, we'll do a reminder. Let's first look on an example of second order differential equation. I think it's a nice way to present the Wronskian. And then we will look at the nth order just to generalize things. When you will see that, you will know what to do. But for our purposes, mostly we will need for second order. Most of this course will be about second order differential equations. We will have some other things, but a lot of the course will talk about second order differential equation because that is not exactly solvable. If we will look on first order linear differential equation, we know the general solution, so it's not interesting. For second order differential equation, we don't know the general solution, so we have to do some tricks. And that's what we will see at least at the first section of the course. We will progress in the course and we will see what will happen next. Now we will decide. Okay, so second order. General solution, we call it Y solution, we look like C1, Y, H1, plus C2 y H2. We are talking about homogeneous, okay? If it's non-homogeneous, we will have another term that stands for the non-homogeneity. That is a real word, right? It's a little bit strange. Okay, and we will need to take care of that, but for now, it's the homogeneous stuff is enough to present the Wronskian. Okay, and what it means to those functions to depend on each other. There exists a constant. Let's write it. Let's write with one constant that yh1 will equal c is the constant, c times yh2. Okay. We want to find something that should be equal to 0 if and only if the solutions are dependent on each other, and therefore we find only one solution. When we have second order differential equation, we must have two solutions, and if the solution we find are dependent on each other, we actually find only one solution, right? Okay, so yh1 divided by yh2 equal to c. If we will take the derivative of this, what we will get? yh1 yh2 tag minus y, actually it's here the tag, yh1 yh2 tag divided by yh2 squared equal to 0. Multiply both sides by yh2 squared, we will get y tag h1 yh2 minus yh1 yh2 tag equal to 0, and that's like writing the determinant. I will write it with straight lines. Okay, everyone familiar with that notation? Y, and let's write it a little bit different. We can multiply by minus 1, okay, just to give it the form of the usual Wronskian. And now we get that equation equal to the equation of just doing yh1 yh2 yh1 tag yh2 tag. Remember, all of those functions depends on x, and therefore the determinant is also dependent on x, right? And if for all, that stands for all x in the domain it's equal to 0, we got that those two functions are depending on each other. Equivalently, we have that if for one point it's not 0, so if you find one point that the determinant is not 0, those functions are not dependent on each other. Is it clear what I did for now? Okay. And for nth order differential equation, it's just taking that determinant, the same test for second order, that will be the usual test we will do. It's actually a nice validity check that you find two solutions, right? Not just one solution. Most of the time you will see that, but maybe when it involves some trigonometric identities, you will not find that so easy. That is just one example. There are much more examples that it will be sometimes not clear. Okay, so the Wronskian usually note with W of function y1 to yn is just the determinant of y1 ta 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 to yn, and then y1 and derivative. Everyone remember that notation? Ta 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 yn and derivative. Okay? Is it clear? And when you have some dependency,
It should be n minus 1.
for nth order, let's write it with capital N, because I write it there with capital N.
It should be n minus 1.
Why?
Because you have the zero of the zero of derivative on the first row.
Right. Is that a mistake also in the
No.
tutorial notes?
No, I've checked.
Okay. Nice. And what, by the way, what it means to have dependency with n functions? There exists n constant. You multiply each function by a constant, and then you get the zero function when you sum everything up and the constant's not equal to zero. Everyone remember that from linear algebra? Someone not remember that and need some clarifications?
Can you repeat?
What it means to have a dependency between n functions? That means there exists n constants, let's say I from 1 to n, that yi, the function, the I function, will be 0, and there exists I such alpha I is not 0. So it's not a trivial sum. Yeah, you can, if this thing were not here, I could just take all alphas to be 0, right? And then I will get all functions are depending, and that is nonsense. Okay. So now we can actually, and if for all points it's equal to 0, that means those functions y1 to yn are dependent on each other. Okay? What?
So if they dependable with each other, just fix you take the first homogeneous, and the second one is the first homogeneous.
Again,
multiply
can
by
you
this.
repeat?
You have in Hebrew it's called nivun. You have nivun, and everyone is dependent.
Degeneracy. No, it has nothing to do with degeneracy. It's actually just, do you remember from linear algebra dependency on of vectors?
Yes.
It's the same thing, but now not vectors, functions. It just means you find the same form of solution. Remember, general solution, for example, for second order OD, will be just choose any two constant you want, and you find the general homogeneous solution, right? But if those functions are depending on each other, assume it's with 1s or 2? 2, okay. Assume DP, dependency, okay, of y, let's say y2 and y1, it's the same thing. You will get C1 yh1 plus C2 times C, just the constant, yh1, and then you can just take out the YH1, C1 plus C2 CYH1, and then you can clearly see you find only one form of the solution because it's equivalent to write just an arbitrary constant, let's call it C tilde, times YH1. So it's just, and then you find only one, and that is second order differential equation, so you are supposed to have two solutions, right?
But if you, okay. But in the degeneracy case, it's the same thing, no? No?
No, degeneracy means you have two values that are the same.
Degeneracy, for example, in quantum mechanics, it means that two eigenfunctions are presenting the same, for example, energy level. That doesn't mean they are depends on each other like vectors dependency. Okay? Come to me after, I want to continue. If it's still not clear, you can also send me a mail. By the way, I should publish my mail or we just open a WhatsApp group? Kalinsky will open. Okay? Nice, Kalinsky. Thanks for doing that.
There is already a group.
What? Already a group, so just join. Add me to the group.
Yes, I'm not sure if everyone will be here.
So just add me. You can. I prefer to not send me messages on things on that for this course in private chat. But if it's an emergency, you can do or even call me. It's okay. We don't have that many students, so it's okay. But I prefer for the course, if you need some extension or things like that, just write me a mail and it will be much quicker for you, because when I'm reading mails, I'm usually from the computer.
So what's your mail?
My mail? I will write it in the course webpage, okay? Okay. Boundary conditions, that's what we talked before. Lichtler and Neumann, everyone knows that. I wrote it, okay, I think I already wrote that thing. There could be also some mixing boundary conditions. For example, y3 tags at 0 plus y at 2 equal to 0. That could be also a boundary condition, right? It removes 1 degree of freedom. Okay. Okay. Solving ODEs with constant coefficients. Okay. So ODE is with coefficient. Okay, if you already, for example, let's look on the second order because that's what we will usually see in our course. We'll have the form of A, y2 tags plus B, y1 tag plus C equal to 0, y equal to 0. they're homogeneous. Usually if they are not homogeneous, we will see how to find also the non-homogeneous term. Okay, that is the second order case, and in the nth order case, wait, everyone familiar with span? Yes? Span. Span like vector span? Now I want to use it for functions. Okay, I will not bother you with that. N times 1 I am writing it with N and I where AI equal const. They are just constant functions. Okay, by the way, without losing generality.
Without loss of generality, and you should start with zero.
Yeah, you're right. Without losing
without loss of
generality, we can say, for example, that an equal to 1. Why?
You can divide.
We can divide by it, right? Do you agree with that? Okay. Okay, so, and how do we solve those kind of equations of these?
Characteristic of polynomial.
Yeah, and how do we find it?
You assume that y is equal to...
We assume a solution that in the form of y, let's say mu x, okay? And we find that the characteristic polynomial, every time we take the derivative of y just multiplying by mu, therefore the characteristic polynomial is just, the general one is ai mu to the I, not the square root of -1, right? If someone has problem with that, they can use J, and I think there is no engineers in here, so we
because
should
engineers use J instead
of I. Instead of I. Yeah, that's just nonsense.
A bit stupid.
Okay. Maybe I should not say that when the recording is on, but yeah.
It's okay, we'll send them.
What?
We will send all the engineers.
Very nice.
Video.
Send all the...
Okay, and the roots, what are they presenting? A unique solution, right? But what happened when we have repeated roots? For example, the characteristic polynomial, let's write in as his multiplication form, okay, of mu minus mu 1 to the R1 is just, okay, right, mu minus mu 2 to the R2, go with that, minus un to the Rn equal to 0, because we want to find when it will be equal to 0, right? When R of I, let's take it, is let's say bigger than 1, bigger by more than 1, it's a natural number, right? Okay. There is degeneracy, some sort of degeneracy. It's not actual degeneracy like in quantum mechanics in energy levels, but it's some sort of degeneracy from the characteristic polynomial. Okay? If, for example, why I call it degeneracy, because all the solutions that have that mu will decay is pretty much the same. Okay, maybe a polynomial difference is nothing. Okay, it can be a lot. Okay, if it's very big. And how it will look? Let's assume we have. Let's assume mu equal to, give me nice name for a root that is not R. Rho, okay. Rho is a root of the characteristic polynomial, okay. That repeats repeat is like that, right? Yes? Repeat n times, okay, never mind. N times. We want to find all the solutions that have that row in the exponent. We just I put it in the tutorial lecture note. You can see it's just multiplying by x each and every time. So the first one is e to the row x, because the second one is x e to the row x, the third one ta 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 ta. And then if it repeats n times, we have m minus 1 e to the row x to the m minus 1 times e to the row x. Any questions? Okay. So let's do our. What is the time? Okay, very good stuff. I'm actually faster than what I thought we will be. So if I'm too fast, tell me. If no, it's okay that we will finish early. That is just a recap on things, so I maybe should expect that to be like that. Okay. So let's do. I wrote where all of those other solutions came from in my lecture tutorials. They publish on the course web, so you can find that there. You saw that already in the OD course. So, okay. That is actually a question that Snell gave me. It's a nice question. He talks about the model of the springs under your car seat. So every time you drive and you driving on a bump on the road, there is a spring that attached to your chair that pretty much absorb the impact of the bump, and we want to find, okay, and maybe I should say that it's in a medium, so it's not ideal oscillator. You have also some damping, and we can control the damping like we will see, and we want to find the ideal damping coefficient that okay, that is just the background. So our model goes like that. I will write it here and remind me to, after that, put the board on top, and I will write only on this board, so it will be appear the question. Okay, I'm writing in English, so I need to get used to that side of the board. Okay, question. we have a car seat. Let's draw it. And I am sitting here, hopefully not driving this car, then it will not end well. I'm joking, I'm a good driver.
Of course.
Trust me. Always passing with red lights, right? For me it's green, I'm so fast.
It depends on speed because of
Yeah.
some effects.
Yeah, okay. So, and here we have some spring attached to our chair. And here we have a bump in the kvish. Okay, I said that in the bump. And when we are driving on that bump, the spring gets shorter and start to oscillate, hopefully not too much, and just once, just one time, and expand. That's what we want. So the first question is, we're saying that, okay, let's say one thing before. How do we control in the dragging coefficient? Let's try the harmonic oscillator equation. Everyone familiar with that? If not, get out. I'm joking. That is graduate course. Of course you are familiar with that. Joking. You... I'm joking. It's okay.
No.
Are you familiar with that equation? Okay. Nice. You see that everything here is constant. All the coefficients are constant. What is omega?
It's frequency of oscillation.
Right. And what is the equation that presents it? Omega equal to?
Square root of k over n.
Right. When k is spring constant and m is
The mass.
Your mass.
The mass
of what?
Fields.
of the
car.
car. Of course it has
Okay, what attached to the car, but for modeling this, you mostly, okay, maybe the driver, but the
mass of something.
The mass of something, it's
cube. Perfect.
approximately proportional to the mass of the car. Let's continue with that. It's assumption of the model. So I will just use m as the mass of the car. It's a good model. Trust Schnell. Okay? If you're not trusting me, trust Schnell. If there is any problem, blame me. I'm joking. Okay. So, the first question, if we add a thin layer of oil, what will change? I already told you. Let's what will change in the equation? We will add a thin layer of oil on the spring. That's right. Assume that we add thin layer of oil. Let's see how I wrote it in the which coefficient will change?
Friction coefficient.
B.
Which coefficient will change?
B.
The friction
B.
coefficient.
And how do you explain that?
It's the friction.
The friction. It's
Yeah, you add a thin layer of oil. Okay, we'll just say it in words. If someone needs to see it written, you have the tutorial sheet. don't want to spend time on this. Okay, if you add a thin layer of foil on top of the spring, you're not adding too much mass, so M is not changing. You didn't change any properties of the spring, right? To change K, for example, you can use some thermal stuff and the K will change, but we don't do that when we add a thin layer of foil. And just we add some another interaction with the medium, so B's change and some viscosity stuff of the oil, and all of those stuff will determine B, right? So we're saying words. This section is done. The second one is examine the different ranges of damping coefficient B. Describe what happened to the motion in each of these ranges. Do I need to do that section? Someone need a reminder of damping, overdamping, and all of that stuff? We'll just write very shortly. How many cases there are? Three. Okay, let's write case. Wait, how do we find them? We did it right now. We just substitute x will be e to the lambda t, and then we find the characteristic polynomial. We solve and find that lambda is going like minus b divided by 2 plus minus square root of b squared minus 4 omega squared, right? So what happened here? We have three cases that determined only on the discriminant, right? Let's note that by d. That is d squared minus 4 omega squared.
Bigger than 0
is 0 or smaller?
What?
Bigger than 0 is 0 or smaller than 0?
Right, exactly. And let's see how the case of B is the discriminant is bigger than 0 for. Hint, it starts with over.
Overdamping.
Overdamping. Over. Okay. When it's equal to 0, someone remember? I will draw a sketchy graph after.
Okay.
I will just do an arrow to the graph. Okay? Or I will do this wise stuff, and then I will just write I or I. Someone can explain the joke. Okay. It's a pretty bad joke. So d equal to 0, it's critically damped, right? Critically damped. How do I write that? Critical. Okay. And the last case is underdamped. Let's write that underdamped, and that is just under down. Okay? And we will show the extreme case scenario of each graph. How I will look like. Let's just say that is the time axis, and that is the x-axis. I is overdamping, we have just decreasing. Right? Do we have a diverging mode?
No,
Why?
because we're in the homogeneous case.
Homogeneous case. Okay. There is there are stuff that happen when it's not homogeneous, but for now I'm just talking on the homogeneous.
Oscillate.
What?
It oscillates in overdump and
Wait.
overdump and
No, for overdamping, B is bigger than omega, so that thing will be negative, all the eigenvalues. That's why if everything is converging and go to zero, that's why it's called overdamping, because it's doing that exponentially.
But shouldn't it also oscillate while decreasing?
It can do so. Okay, let's assume positive coefficients, and therefore it will not happen, right? If you take the derivative, it will be never zero. If you do some decreasing and all of those stuff, okay, I'm not allowed in that. Okay, it could be, the position could be negative, and I choose my coordinate to be always positive. So I'm not allowing that. I'm just drawing one sketch. For sure there are more than one way to draw this, but okay. And it will decrease exponentially. It will be a sum of two exponents with negative coefficient in the power. Okay, the second case. What happened there?
Flat.
It's not flat. It's actually something that will look like that, because the solution is a plus bt e to the minus b over 2, critically down. Right? That is another solution. We showed that before. And that is the lambda. Our lambda is minus b over 2. And okay, nice. The third one is a little bit different. D is negative, therefore lambda is complex. Let's write without r. It's not real, okay? That is just fancy math way of writing it. If someone wants me to remove that from the board because we are physicists, just tell me. I will not tell you it's pure imaginary. It's not a real number. Great. Okay.
Now it will oscillate because it's a complex number, so
it's a complex number, so lambda, it's called, wait, let me explain. Lambda will look like, there's actually something that called the frequency of oscillation in the oscillator, and it will be defined as omega d, and it is just 2 over 4 omega squared minus b squared. It's only for the underdamped case, okay? And the general expression of lambda is minus b over 2 plus minus omega di. That is the rate of decay, and that is the frequency of oscillations, right? Because Euler identity. And then if I will write that, it will look like, let's say, we have some exponential decrease, right? And we want something like that to happen. And which one is the most comfortable chair?
The first one?
The first one?
No. The second one.
Why?
Because
it goes with the bump, that's what you want to say, but it's actually it's not so easy to see. It's the most comfortable one because it comes back to where it was the quickest. Why? That decrease like minus b over 2. Okay? That is actually the third section of that question, is which one is the most comfortable. You don't want any oscillation, so that is forbidden. And you want your chair to be back to its place as quick as possible. So why that? Do you need the faster? Here we have two eigenvalues. One in absolute value is smaller than b over 2. Okay? That means, for example, let's look on that. It's actually lambda, let's call it lambda mean. It's actually the one that's smaller. So, I'm sorry, the one that is bigger, but in absolute value it's the smaller. Okay? Let's write it with absolute value. And absolute value on that also. b over 2 plus the square root of b minus 4 omega. But what happened in that case? Asymptotically, I saw that Snell told you about some asymptotics. Asymptotically, it will be exponent with e to the lambda mean t, right? Because the other one will be already negligible because it has smaller or bigger in absolute value eigenvalue, right? Is it clear?
Yeah.
Polinsky? Dima, right? Okay, you told me once and I remember it.
You won't remember
fine.
this. Next time you won't remember this.
Okay, if
It sounds like a challenge.
if you're wrong, what you give me?
Nothing.
Okay.
I
I have nothing to talk with
I
you.
will give you respect.
You will give me a respect, okay. I will take that offer. Okay, and that thing will decay much faster than that. And therefore, even so we have that linear term, exponent will win, right? We saw that in Math of Physicist 1 or in Calc 1. Right? Everyone agree with that? How do you prove that? That is not the material of that course, but you divide them both and use L'Hopital's. Okay, very nice. Okay. And then you get that decrease the fastest, and that also goes with the bump, so it's the most nice case. And the question is actually find the relation between b and omega, so it also say that, okay, equivalent is much nicer, so we get equation of d equal to 0. Therefore, we get b squared equal to 4 omega squared. Right? Do everyone agree with me?
So b is plus minus 2 omega.
Yeah, but minus 2 omega is forbidden, right? Negative damping coefficient is just not physical.
Yeah, so
Okay, it's just 2 omega. Because omega is also positive,
yes, of course.
there is no reason to look at negative omega, just choose your axis right. If you will flip the x direction, it will actually flip your omega, right?
Of course, there is no such thing as negative
Yeah.
friction, but we don't know this.
Okay. And now the last question is why there is a limit. Everyone that has a driving lesson, there is written the limit of weight on the car. So Kalinsky could not join your car, right? I'm not calling you fat, I'm calling you massive. Okay.
Massively also.
Wait for me.
we will see, Kalinsky. Okay, so what we're trying to see is why there is such a limit. That is not so intuitive for me, but when we really look at that model, we see that there is dependency on the mass. Of course, that is oscillator. Most of the time, oscillator and spring have also the mass attached to them, right? So if, let's fix B at 2 omega, let's call it omega 0, okay? I need more space, so I will just
I know there is there are the homeworks and there is the test, but are there quizzes or in the
I don't think so. You need to ask Snell. He's the one that.
הוא אמר שיש 80% מבחן 20% שווא.
אז לא יהיו בוחן.
There will be no quiz. So if Snell says, Snell knows. Okay, that is the rule for our course. Okay, so the last sub question is why there is limit to the mass. If we, let's say we had a mass, our mass now is m plus mc. Kalinsky, that for you. If Kalinsky join your right, what happened here? Let's say the omega 0 is our first term here, and omega final, let's call it, it's, you see that is capital N, because that is very spiky.
What did you write over there?
What? Here?
Yeah.
Capital M equal to M, let's write M initial.
No, that's
and
a
then
U, an L.
What?
שווה, זה שווה, ואז
לא, לפני זה.
אחד לפני?
That is D.
זה D. Okay.
Yeah. You have some small loop and flip there. Unfortunately, that is my handwriting, so okay. For now, I'm not willing to change it. Square root of k divided by m final. We know that m final is much bigger. Is bigger than mi, therefore omega final is less than omega 0, right? So omega decreases, but B is fixed. So what happened to if and and equal to b equal to 2 omega. Okay? Because, like you say, b squared equal to 4 omega squared. Therefore, we got that, and omega 0. Right? Okay. So now what happened? What happened to this discriminant?
We come to the discriminant is now greater than 0.
Right. Now, the discriminant is bigger than 0. So, our case now is overdamping. Right? We switched from critically damping to overdamping. That means, like we explained before, that our churn returned to equilibrium much slower. Right? And if another Kalinsky joined the car, okay, now it's really heavy, really heavy. So our shell will take him more and more time to come back. Snurb started to tell me something about tanks and this effect, but I will let your imagination think what is the relation between tanks and springs. I don't have a clue. Have someone felt that in the car? No? That means you didn't give a variety to Kalinsky. I'm sorry, Kalinsky.
Felt what?
It will get back to you.
Yes. It was a question. You wrote the mass of Kalinsky with a C. Kalinsky is not with a K?
No.
Really?
You got it wrong. You got it right. All of it wrong, but the name is right.
Okay. So from now we will talk about Euler-Cauchy equations, if you remember. It's maybe also called equidimensional equations. Does someone know what that thing is? You know? Another one? You know? Okay. It's when the time, okay, how do I explain that? It's the number of derivatives match the degree of the monomial that is multiplying. I will write it. It will be much clearer. We'll just clean the board. That door is working now? Oh my god.
I think it's working only in one way direction.
Oh my god. I think all of my bachelor studies were locked. Right. In the last 3 years it were locked. I'm not crazy.
2 years. It wasn't exist 3 years ago.
What? What?
This room is only 2 years.
Only
זה
2 years.
באופן רקע, אז
When we was on first years, the room were not.
Did not exist.
That's interesting. No, that is not right because on the second semester I had the tutorial series.
נכון, היה לנו פה סטטיסטיקה.
החדר זה היה קיים פשוט הלוח היה שונה.
And the chair.
Okay. So Euler-Cauchy's equation is equation that's right the second order one. Coefficient A, x squared, y2 tags, plus bx, y tag plus c y equal to 0. For now we're only talking about homogeneous equations. The thing, how do you find here the characteristic polynomial? You substitute function in the form of x to the r, right?
I know it.
Everyone familiar with that?
I know it in another form of solution, which you make x equal e to the z. If
X is e to the z. Okay, it's okay. You can do it like that. That's how you prove that substitution. But it's much easier to do it like that, right? You just substitute x to the r, and then you can just divide by, for example, if it's the second order differential equation, you can just divide by x to the r minus 2, right? And you get all the r's because you get the characteristic equation, right? So it's much nicer than you do some substitution. That's why we are doing this tutorial, to make sure that everyone is on the same line, because from here it will get much complicated in the differential equations, but it will get much cooler. I brought another equation that I wrote 10 minutes before I got here, so it could maybe a little bit show you why the course is nice, because there's some nice mathematical stuff that can also help us in physics. My question is not about in physics, but it's nice math. Okay, so I bought it. It's nice trick that can also help you in physics. Actually, I think I used it once in stats test, so it's nice. Okay, y equal x to the r. Then we find the characteristic equation. Okay, how do you prove that is a nice thing? You just substitute an infinite power sum, right? And then you get a relation that will fix some n's, right? And what happened if we have repeated roots? Let's say we got P of r is our characteristic polynomial equal to 0, and we have r equal to r0 that we repeat m times. That maybe if someone studied OD last year, he didn't saw that. I think only Ronnie showed that. So if you didn't study with Ronnie OD, you maybe never saw that. Then what do you do? You have m solution x to the r0 log. Okay, if in my I think I wrote here log instead of lan, but log, if you're not writing the base of the log, I mean lan. I study in the math department, I'm sorry. Okay, lan of x to the r0. Actually, also Kessler sometimes wrote log instead of lan. But he's also kind of a mathematician. Wait. L of x and minus 1 times x to the power of r0. right? Did someone knew that before? Okay, it's nice. If you want some intuition, it's actually can come from if you have x to the r0 plus, let's say, some small alpha, you do, okay, there are difference, there are x to the r0 and there is another solution. What is x to the alpha? You can write it x to the r0 times e to the ln x, and then just do Taylor, and then you get x to then alpha ln x, and then you got the behavior of that. That is a very nice way of seeing that. And guess what? If you take in the next order, what you will get? Ln squared. And if you can continue, and that is nice way to, in an intuitively way to think about it. Okay. I will also talk about nice trick for integrals if I will have time, and if not, I will take some of your time. Okay, there is quick exercise on that, and the general definition of nth order differential equation like that. Someone need me to write that? It's written also in my tutorials, and I don't think I gave you in the homework third order of that thing. It could appear, but I don't think so. If that will be the differential equation in the test, you should be very happy. Okay? Let's write the question I want. I thought of a nice question. It's actually in the end of the tutorial, but I prefer to first do it and then see if I have time for the variation method. Okay. So assume you have a power sum. Okay, let's give the full background story. I don't know how many of you ever thought on just fix some derivatives or give some boundary conditions and see if there is unique function that behave with those conditions. So my condition is for all n, the nth derivative at 0 is just fn. Someone know what is fn stands for? No? Fibonacci a number. Is everyone familiar with Fibonacci series?
Hope so.
There is someone that is not familiar with Fibonacci series. Okay. It's just the series that start from f0 and f1. I'm writing the most general way of writing it. It's just two constants, and it's behave with that condition. Okay? And now we need to find a function that behaves like that. The actual problem in the tutorial presented find an analytical way of writing the function, and from 0 to infinity of f of n divided by n factorial x to the n. Why those writing are equivalent? Taylor expansion, right? Everyone agree with me? You agree with me? You can do it also for e to the x. You just set all derivatives to be 1, and look what happened. It will be very cool, I promise. And for now I'm doing a harder case because we don't have time for the easier case. But it's the same, and it's just the concept that is hard. That this question is equivalently hard as the other question. How many constants, how many degrees of freedom we have here? The recursion relation gives you two coefficients, right? f0 and f1. Do you agree with me? So if I will try to take it to the ODE world, what will be the order of the ODE? You can guess. 2. Okay, because we have 2 degrees of freedom. If we will have more than that, we will need to say which solution is invalid at the end, right? Because we have only 2 degrees of freedom. Let's take the derivative. The derivative once, you get n minus 1 factorial, f to the n, x to the n, minus 1. Let's see. Okay. Okay, and that equivalent to write fn plus 1 from 0 to infinity, right? And factorial x to the n. And y, 2 tags, will be the same, but fn plus 2 divided by n factorial x to the n.
But fn plus 2 is fn plus n plus 1.
Right. That is from the equation relation, what we get. We get that is fn plus 1 x to the n divided by n factorial plus the sum of fn divided by n factorial x to the n. But what is this?
Y tag.
Y tag, right. And what is this?
Y.
Y. So we got y2 tags equal to y tag plus y. And actually, when we convert that to be an ODE, we can actually find the function that presents this thing, right? That is very cool, if you ask me. That is a way of, if I will give you a summation and I want to find it analytically, okay, that is a nice way of doing that. We will see in the course, we will have other approximation methods that will be very nice for doing that, but we will see. Okay, if we have them. By the way, we will get 2 general coefficients, but we need to match those coefficients to those 2 coefficients unless we will have 4 degrees of freedom, and we don't have, right? So we will have some boundary condition that we can actually see here. We have infinite amount of boundary condition, but we have only 2 independent boundary conditions, right? That is a nice thing. So what is the next step? Just substitute e to the rx. Yeah, y is in the form of e to the rx. Then we get r squared equal to r plus 1, right? That is the characteristic polynomial. And then what is the roots? R1, 6, 2. Okay. We get minus, not minus 1. 1. We move things to the other side. Plus minus square root of 5. Right? Everyone agree with me? Okay, very nice. So the general homogeneous solution is A e to the R1x plus B, let's call that E R plus and R minus, just because we can. How do we find the exact coefficient? It's very nice. We use y0 is f0. Let's for now use the regular way of regular series of Fibonacci. What is f0?
1.
0.
Ah,
We
okay.
will start from 0, and y1, the first derivative at 0, is f1, that is 1. Okay, if you will choose it also to be 0, you will see you will get 0, but that is just ridiculous to do that. Okay, so now we will set things up, and we will get that from the first equation we get a plus b equals 0, and then a times r plus b times r minus equal to 1. Then I will do something that's very fancy mathematically, but I will recommend you to remember. You can write it in a matrix form. Why I will do that? Because then you can just remember very easily the general solution of a non-zero determinant of that thing. What happened if the determinant is 0? You see that r minus will be equal to r plus at that case, and then you will need to do some other tricks we already showed, right? But for our case, r plus and r minus are not equal to each other.
Why 1?
What?
Ah, 0.
So if you remember the formula for the inverse matrix, it will be just taking the inverse. And I will tell you r plus, I'm sorry, a will be 1 over square root of 5, and b will be minus that. In here, there is actually no reason for doing that, because this is very easy to solve. Yeah, a equal to minus b, so it's very easy. But if you have general equation, I recommend you to remember that, because you will not have a lot of time in tests. Okay, so it's very nice to just remember, I know that, and because we're only dealing with second order differential equation, okay, not only, but most of the time, it's useful for that course. So I really recommend that. And then what we got the exact form of that function. I'm taking your time a little bit. We get that 1 over square root of 5 times e to the 1 plus square root of 5 x minus e 1 minus square root of 5 IV2 times x. And now we finished the tutorial, but one more nice thing that you can do from that, you actually know that the nth derivative at 0 is equal to nth Fibonacci number, so you can actually get a general solution for nth Fibonacci number from that. That is a very nice way of showing that. Why? Because taking the derivative of that thing n times is very easy. Let's do that. N time 1 over square root of that. Okay, 1 plus square root of 5 divided by 2 e to the n. Let's just substitute 0 already, okay, because I'm lazy. Don't want to write the whole expression. That will be with minus sign. That will be put to 0. That is the general form of Fibonacci number, because at 0 that also equal to the nth Fibonacci number. So that is a very nice way of using ODEs to find general solution for nth Fibonacci number. That is just a bonus. And yeah. Okay, so we finished. Next time we will do some variation methods. We will publish that, and regular singular points, and a lot of those stuff. It will be fine. And then we finish with all the refresh from the ODE, and Snell will probably start doing the real material of the course. Yeah, the heavy stuff. That course is actually not that hard. I think so. But not supposed to be.
The most heavy stuff in this book is you.
Yeah. And you. We talked already about what happened when you were taking a ride, right? Okay, so I think we finished. Let me know if there is any problem in the homework or something. I will fix that and let you all know. There is not supposed to be any problem, but we never know. I wrote them at 1 in the morning, so I will not be surprised. But there are not. I already wrote solutions to the homework, so.
Can you find them?
What?
Can you find them?
Only to you know. Okay. Any questions? I'm here for the next 15 minutes.
So basically,
Because
you showed the way how we can find the nth Fibonacci number, right?
Yeah.
But for example, computationally, it looks not as